Hi everybody, I hope you're all doing well. It's really nice to be able to talk to you again, even if it's just recording a video. I hope this video is going to be useful. It builds on the previous video I made that focused on building the baseline scenario, how we made assumptions about how energy demand was going to change into the future. In this video, I want to continue talking about the baseline scenario and specifically how we can create the baseline scenario in LEAP for electricity generation from the excellent data that Emily sent to me. The second thing that I want to do is then show which of the mitigation measures in the comprehensive document that Emily put together, which of these mitigation measures we are able to model in LEAP to look at what effect they will have on black carbon, short-lived climate pollutants, and air pollutants. So let's start. I've got a lot of tabs open here, but let's start with the electricity generation baseline scenario. So the data that Emily sent was really good and really detailed. We have projections from 2020 to 2029 for generation of electricity using different types of technologies and using different types of fuels. If we go back to LEAP and look at our current account, which is our historical period, under the electricity generation branch, we tell LEAP what percentage of electricity is generated using different types of fuels. So I focused on the information that Emily provided on the electricity generation by different types of fuels to create the baseline scenario rather than the types of technologies. So this is how I have done it, because it's then consistent with the historical way in which we've looked at emissions. If I go back to LEAP, you'll notice in the current account, the information that we need to put in is the percent share of electricity that will be generated using different types of fuel. So the information that Emily provided to me was the number of gigawatt hours, the number of the actual amount of electricity generated in energy units. That's fine, but what we want to make sure is that there is a link between demand for electricity from the residential sector, from industry, from services, and then the amount of electricity that is generated. So what I then did was, instead of entering this amount of electricity generated directly into LEAP, what I did was calculate for each of the 4 scenarios Emily sent me the percentage of the total electricity generation that will be generated using different fuels and different technologies. So, for example, in 2020, it's estimated that there will be 7,700 gigawatt hours of electricity generated using natural gas. That works out to 37.8% of the total electricity generation. And it's these numbers that I want to enter into LEAP to continue that percentage share into the future. So I'm not entering directly the electricity that will be generated. That number will come from the electricity demand, from the demand for electricity from different sectors. What I'm doing is saying, based on that electricity demand, what percentage will be generated using different fuels and different technologies. I hope that is clear, and I hope it makes sense. The next thing about Emily's data is that there is 4 scenarios that are included here. And if my Spanish is good enough, the first scenario is that new projects are put in place on the date at which they have currently been said that they would be put in place. So these new planned projects will be put in place at the right time. This scenario here, as far as I can tell, represents the scenario with the highest level of renewables. So by 2030 in this scenario, we have 18% of our electricity generated using solar, 6% using wind, 5.7% hydro. Scenario 2 and Scenario 3 are very similar to Scenario 1, except there is a 6-month and then a 12-month delay to the projects. But in 2029, there's no difference really. You get to the same point in the end, it's just slightly delayed. Scenario 4 is quite different. It supposes that these planned projects do not happen. They are not implemented. And in this case, we have much less of the solar project. So we only have 7% of electricity generated from solar compared to 18%. So this is the least ambitious or the most pessimistic scenario. In order to be able to capture the effect of having these new solar projects, I have chosen this scenario as the baseline. But you can tell me if that is incorrect. I've chosen this scenario where the new projects are not implemented as my baseline. And then I've put in scenario 1, where we get much more solar, as one of the mitigation scenarios, assuming these projects go ahead. So that's the first thing. So I then want to also ask you a question about the data that was sent. So you can see here that in 2020, it's estimated that there will be 37.9% of electricity generated using natural gas, which is 7,700 gigawatt hours. Then there will be 1,294 gigawatt hours using oil and 8,000 gigawatt hours using coal. In 2020, those are the main fuels used for generating electricity. And I just want to highlight that they are different to the historical data that came from the National Energy Balance. I think there may be a mistake in this data. If we look at the data that comes from the National Energy Balance for 2018, so the closest year that we have, there was 8,200 gigawatt hours generated from fuel oil. And you can see here that there's only 1,200 gigawatt hours generated in 2020. If we look at coal, there is 2,200 gigawatt hours generated in 2018 and 8,000 gigawatt hours generated in 2020. It seems unrealistic to me that in the space of those 2 years there would be a fourfold increase in electricity generation from coal and a fourfold decrease in electricity generation from crude oil. My suspicion, I think what has happened is that these two have been mixed up. That this value here should be for petroleum and this value here for carbon. But that's something that I want to check and make sure that that my thought is correct. What I have done is entered this data. I've entered this data into LEAP to create the baseline scenario for electricity generation, assuming that this value here is for heavy fuel oil, for petroleum, and this value here for coal. And that creates something that is more consistent with the historical data from the energy balance. So this is my current account. We already entered this data and we did it in Santo Domingo, I think, last year. For the baseline, I've then entered the data, and what I've done is simply copied and pasted the data from LEAP like we've done many times before. So for natural gas, I just copied these two rows and pasted it, and then LEAP puts it into the format that is useful in LEAP. And you can see I did that for all the other values. For coal, I used these values here. I assumed this was the value for coal. And this was the value for petroleo, or in LEAP, heavy fuel oil. And I added in the hydro and the wind and the solar and the biomass, which I assumed was bagasse. And that gives us this projection into the future, where we continue to use natural gas, continue to use heavy fuel oil, and there's a little bit more wind and a little bit more solar being produced. So that's how I entered the baseline scenario for the electricity generation. So now I have a really good baseline scenario for my energy demand and for my transformation. If I click on results, I can then begin to look at my projected emissions into the future and how they are likely to change. We can look at how they're going to change in relation to population, to GDP, in relation to the projections made in the energy demand prospectiva and these electricity generation values. It takes a little while to calculate, so I'm just going to keep on talking while it calculates. The next thing, while we're waiting for to view those baseline values, I went through the document of the mitigation measures that you had identified, Emily. Okay, I think it's finished now. Yes, I'll get back to that in a moment. So now we have our historical emissions from 2010 to 2017 of different greenhouse gases, of different pollutants that we can look at. We can look at carbon dioxide, methane, N2O, carbon monoxide, VOCs, NOx, and then particulate matter, black carbon. We can look at this for our historical years, and we can see that the residential sector, industry, waste and transport are our largest sources. And then we can look at how the values are likely to change over time. For black carbon, it stays relatively constant. And this is because there's a reduction in black carbon emissions in the baseline for the residential sector as people naturally switch over from using biomass to using LPG and other fuels for cooking. But that is compensated for by an increase in industry and a slight increase in waste, and things staying constant in transport. If we look at carbon dioxide, we see a much bigger increase. And that increase comes from electricity generation. We're still burning coal, natural gas, petroleum, oil, also coming from transport as well. There are two largest sources. Industry comes in second for CO2. Methane, as you might expect, agriculture and waste are the two largest sources. Nitrogen oxides, another air pollutant, transport, and electricity generation. So we can look at our different trends. Some pollutants are increasing more than others, depending on what the contribution of different sources are. What we want to do now is to look at implementing our mitigation measures to be able to see how much we can reduce these increases by implementing different mitigation actions. So as I think we talked about in the last call, I went through all of the mitigation measures in Emily's document and put them into a matrix of mitigation measures here, and tried to identify which ones we can implement and which ones will be more tricky with the analysis that we have. So we can improve the overall efficiency by reducing the proportion of used cars imported. We can look at that one. We can switch over to CNG, 110,000 vehicles, 108,000 gasoline vehicles. We can look at that one definitely. Bioethanol and biodiesel, we can definitely look at those. Ones that are difficult to look at are the impact of expanding the metro network and BRT system. The modelling that we have isn't well set up for looking at those. Other ones that are tricky to look at is hybrid electric CNG vehicles. This mitigation measure doesn't have a target associated with it. If it said we want 20% of vehicles to be electric by 2030, then it would be much easier to be able to look at. There are then objectives for the tourism sector, like reducing food waste. These are in theory possible for us to look at, but at the moment in the waste sector we don't split tourism waste from other waste, so it's hard to make that distinction. But we should be able to look at that in the future, perhaps, if we can think about some assumptions that we can make. But the main mitigation measures that we can look at from the list that you have here at the moment are doing things in electricity and doing things in transport. So seeing as we've been talking about electricity, let's look at the different mitigation measures that we can have. So in the list of mitigation measures, we have all authorities in electricity will ensure 25% of the service by 2025 are met by renewable energy sources. This is an easy or relatively simple mitigation measure to model. I should tell you first how we can create these alternative scenarios to look at mitigation measures. And we do that in this scenario menu here in LEAP. Scenarios work by, so our different scenarios are connected. Current accounts is our historical period. And that's linked to our baseline scenario. So our current accounts is from 2010 to 2017. Our baseline goes from 2018 to 2030. Before we make any changes, our baseline is exactly the same as current accounts. But we've updated the expressions, as I showed you here and in the previous video, to change it from current accounts, to make it increase in the future because of population and GDP increases. We can then add scenarios underneath the baseline. If I click on the baseline and click add, I can create a new scenario, my mitigation scenario. And that then gets placed in our list of scenarios under the baseline. And what's really important about this is that my mitigation scenario is directly connected to the baseline. That means that before I make any changes to represent my scenario, all of the data, all of the variables will have the same value as the baseline. The reason that is really good is that it means that I only then need to make changes in the specific sector and the specific variables that I want to make the changes in in the specific sector and the specific variables that I want to make the changes to, and everything else stays the same as the baseline. So if I want my mitigation scenario, this scenario here, to only look at the transport sector. I don't need to worry about residential or industry or waste. They will be exactly the same as the baseline, and I just need to make changes in the variables in the transport sector. So that's why that's important. So you can see here that I've begun to create scenarios for those mitigation measures that I think it's possible for us to evaluate. So we have scenarios here: renewable electricity generation. And the renewable electricity generation scenario is trying to implement this mitigation measure. 25% of electricity will be met by renewable energy sources by 2025. That's what we've put into that scenario, and I'll show you how we've done that in a minute. The second scenario that I've created is existing electricity plans. And that one is this scenario here. All plans or all planned changes to electricity generation will be implemented. So that's how we are representing this scenario here. I've then created two scenarios for biofuels. In the list of scenarios, we have these mitigation measures here that want to have an E20 mixture of gasoline, so 20% of ethanol in gasoline by 2030 and 12% of biodiesel in diesel. There's then this more ambitious mitigation measure to have E50, 50% ethanol, and B68, 68% biodiesel, I've assumed by 2030 as well. So the biofuels transport 1 does the first scenario with 20% ethanol, 12% biodiesel, and transport 2 does the more ambitious 50% ethanol, 68% biodiesel. And again, I'll show you how we implemented those in a moment. Then we have this scenario here. So there's multiple targets in this mitigation measure. Improve overall fleet efficiency by reducing the proportion of used cars imported from 67 to 33% by 2030 and decreasing the average age of the automotive fleet from 15 to 10 years during the same period. So I've taken the second part of that mitigation measure because I think that's the one that's easiest to implement and evaluate in LEAP, and said what happens if the average age of our vehicle fleet is about 10 years. That's what's in this one. And then the final mitigation measure that I've included in this data set so far is the CNG conversion. So converting 110,000 and 108,000 diesel and gasoline vehicles to use CNG, 240,000 LPG vehicles. They're the mitigation measures that I've begun to evaluate in this data set so far. I've then added one final mitigation measure here. It's my all measures scenario to give me the overall overview of what happens if we implement all of these actions. This is another thing that's useful in LEAP. We don't need to create new scenarios and new expressions when we want to see the combined effect of everything. We can just create this scenario and add in our scenarios to it. So I've added in my measure to decrease the vehicle age to 10 years. I've added in my mitigation measure to convert CNG vehicles and to have biofuels for transport and to implement my electricity plans. So we'll look at all of those together and give us the overall effect. Okay, so that's creating the mitigation scenarios. Now let's look at how we implement these scenarios in practice. And I'll start with the easy ones, which are the electricity generation ones. So the first electricity generation one is M1, renewable electricity generation. So if I go to a branch that is completely unrelated to electricity generation, for example, urban, you see that all my data here is black. If the text here is written in black, it means that it's the same as the baseline. It's inherited those expressions. They haven't been directly entered. If I go to my electricity generation, I want to change the percentage of electricity that is generated using different fuels. And you can see that I've done that with this expression, and we can see that this expression is new and specific to this scenario because it's written in blue. If I click on Builder, I can then look at this expression. In this expression, it says interp. So this is the interpolate function. In 2019, I want the percentage of renewables in my electricity generation to be the same as the baseline value. In 2030, I want it to be 25% minus the amount that is hydro, minus the amount that is hydro, the amount that is solar, the amount that is wind, and the amount that is biogas. Because they're also renewables, right? So we just want to add to this scenario the amount of electricity, the additional amount of electricity to get to that 25% target. So that's what that expression is doing there. Generate enough electricity, generate enough electricity from renewables to meet that 25% target. My existing electricity plan scenario has more blue to it because my existing electricity plans data has projections for all the different fuels and how much electricity they will generate. I entered these in exactly the same way that I did for the baseline scenario. I just copied these expressions, and then what was that for? For natural gas, and then just pasted the value there for natural gas and for all of the different types of fuel. And look at the graph that we get at the end. We can see that the amount of electricity generated from solar increases quite a lot, and the amount of wind increases a lot. The amount of coal used disappears almost entirely. Natural gas and heavy fuel oil stay significant, but it's quite a different graph compared to the baseline. So that's how we've created those mitigation scenarios. The second mitigation scenarios we created are all for the transport sector. So let's think first about biofuels. There are lots of different ways we could have modeled these biofuel scenarios. So I'm going to go into my transport branch, road transport, and then I have my different types of vehicles here. And I have my projection for the number of vehicles that there will be. And if I take automobiles, for example, I have gasoline, diesel, CNG, LPG, electric. I have my different fuels here. One way I could have modeled switching to biofuels would be to create another branch here for B12 or E20 or the different types of biofuels that are being used. So I could have another branch under automobiles, and that is for biodiesel, bioethanol, for example. I didn't do it that way. What I did was I changed the emission factors. So for bioethanol, I have assumed I've entered an expression to reduce the CO2 emission factor by 20% for E20. So I've assumed that the amount of CO2 that is non-biogenic, that is a contribution to CO2 in the atmosphere that doesn't come from plants and is recaptured, decreases by 20% when you have a 20% mix of ethanol and gasoline. So that's what I've done for CO2. The introduction of biofuels can also affect the main purpose of biofuels is to reduce greenhouse gases by having renewable fuels in the fuel, so that you're not using fossil fuels totally. You have a percentage of renewable fuels in the mix. But there are also effects of introducing these biofuels on other air pollutant emissions, because the properties of the ethanol is different from the gasoline, and the biodiesel is different from the diesel. It burns differently. For ethanol with gasoline, I couldn't find any data in emission inventory guidebooks as to how the air pollutant emission factors are affected. So for switching to gasoline, or switching to bioethanol in gasoline, there is no effect on the air pollutant emission factors. They're the same as in the baseline when it was just gasoline. However, for diesel, we do have an effect. So for diesel in the biofuels transport 1, there's a 12% reduction in CO2 emissions as we go to as we have 12% biodiesel in our diesel mix. But in this document, in the EEA Emission Inventory Guidebook for road transport for air pollutants, we are told the use of biodiesel as a blend may also lead to some changes in emissions of air pollutants. And we have proposed values in this table for the differences in emissions compared to using fossil fuel diesel. So, for example, for particulate matter that includes PM2.5 and black carbon, for passenger cars, if we use a blend of 10% biodiesel, they've suggested a 13% reduction in the PM emissions compared to using diesel from fossil fuels. And for B20, they've assumed a 20% reduction. And we have these for different pollutants. They're not all negative. For NOx, there is a slight increase, a few percent increase in NOx emissions from using biodiesel compared to fossil diesel. But there's a large reduction in particulate matter. So in our mitigation measures for biodiesel, I've taken the reductions that we had from that table and applied them. For this scenario where we go to a mixture of B12, I've taken the values for B10. And for B68, I've taken the values for B20 so that we're not overestimating the benefit, if that makes sense. The way that I've done that is using the same type of interp function. So for NOx emissions, there is a 3% increase in NOx emissions for buses from using this biodiesel, for using B10, and there's a 10% reduction in PM10 and PM2.5 emissions. So what this is saying is that by 2030, in 2019, I want the emission factor to be the same as the baseline value. In 2030, I want it to be the baseline value times 0.9. So I want it to be 10% less than it was in the baseline, if that makes sense. And we've done this I've applied this for all the Euro standards, the same level of reduction in the emission factors, or the same percentage reduction in the emission factors. If you look at the biofuels transport 2, you can see that we get a larger reduction because we've got more biodiesel. Got a 15% reduction in particulate matter emissions and a 3.5% increase in NOx emissions, 15% reduction in VOC emissions, and a 9% reduction in carbon monoxide emissions. So that's how we've implemented the transport, the biofuels measures in the transport sector. This was a very boring job of just copying and pasting these expressions, but I did it for all the different types of vehicles, fuels used, emissions technology, just going through copying and pasting. So I didn't want to do that in a video because you would have definitely have turned off by now. Okay. Now we get to the most complicated measure that we've modeled, decreasing the average age of the vehicle fleet to 10 years. The effect that decreasing the average age of the vehicle fleet to 10 years has, the way that affects air pollutant emissions is that if we have newer vehicles, they will meet more stringent vehicle emission standards. They will have more technologies fitted to them to reduce the emissions of different pollutants. So the effect, or what we need to work out when we have a measure like decreasing the average age of the vehicle fleet, is what does that mean for the percentage of vehicles in 2030 that will meet different Euro standards. So in our baseline, we have most of the vehicles in Dominican Republic being Euro 3 standard vehicles. Few vehicles are Euro 4 and a few Euro 5, and very few by 2018 meeting the most stringent Euro 6 standard. In the baseline scenario, the number of vehicles meeting Euro 6 gradually increases. I'm going to show you how I calculated all this in a minute. I just want to show you, what the effect is in this mitigation measure. We can see that the effect of this mitigation measure of decreasing the average age of the vehicles is we get many more new vehicles that meet Euro 6 standards. So we get, 70% of vehicles meeting Euro 6 by 2030 in the mitigation measure, compared to only about 20% by 2030 if we let things run in a baseline scenario. So these expressions are entered as interp functions, and they're an interp function of what percentage of vehicles meet these Euro standards. I calculated these outside of LEAP, just to make it a bit clearer and to make it a bit easier to do these calculations. The way that I did these calculations was to set up what's called a stock turnover model. A stock turnover model has years down the rows and years across the columns. The years down the rows represent the number of vehicles that were sold in particular year. So vehicles that were sold in or before 2003, 597,000. So in 2010, there were 597,000 vehicles that were sold in 2003. And that comes straight from the data that Emily shared with me. So it comes straight from this data about the number of vehicles that Emily provided. The number of vehicles Euro 4 that were sold in 2004, still there in 2010, 10,000 vehicles, 16,000 in 2005, etc. There were then 2,500 vehicles sold in 2010, 16,000 vehicles sold in 2011, 27,000 vehicles 2012, 27,000 vehicles 2013, 14, 15, 16, 17, etc. So we're estimating how many new vehicles are sold in each of these years. So that's our vehicle sales across this diagonal. What we then do is, if we take the vehicles sold in 2011, for example, is we begin to estimate what percentage of those vehicles are left after a certain number of years. So in 2011 we have all the vehicles left, and gradually they will run. But by 2023 we're starting to lose these vehicles. So by 2030, of the 16,000 vehicles sold in 2011, only 9,000 vehicles remain. Of the 27,000 vehicles sold in 2012, only 18,000 remain on the road, etc., etc. So estimating the number of vehicles left after a certain period of time. And we do that based on something called the survival rate. So the survival rate tells us what percentage of vehicles are remaining after a certain period of time. And I created this survival rate to say what percentage of vehicles are remaining, to estimate an average age of the vehicle fleet that was close to 10. So to try and get an average age of the vehicle fleet close to 10, I modelled how many of these vehicles survive over different periods of time. So that was what I used to try and get this value close to 10. I developed a survival rate. The colours on this chart then tell us which vehicles are Euro 3, based on when these vehicles were introduced. Which vehicles were Euro 4, Euro 5, and everything after 2016 we've assumed is Euro 6, because that's when the Euro 6 vehicles came in. So by adding up the number of vehicles that are Euro 6 and dividing it by the total, as we've done here, we then get what percentage of vehicles are Euro 6 in 2030 for this scenario where we're trying to get an average age of our vehicles of 10 years. So that's how we did that. And then we simply entered those values into LEAP. We entered these values into LEAP. In 2020, we'd have 21% of vehicles meeting Euro 6, then 45, then 76. We've entered those numbers straight in there to represent that increasing number of vehicles meeting the best Euro standards. I hope that makes sense, and after I post this video I'm going to send you that spreadsheet as well so you can begin to look at it. Our final mitigation measure is then converting vehicles to CNG. And here we're working at this level in our road transport sector. We're working at the level of fuels. And we want to write an expression in LEAP that will transfer 108,000 gasoline vehicles to CNG. So we want to write that as a percentage, because what we're trying to do here is to convert percentages. What percentage of our total number of vehicles are of these different types? So again, I've used an insert function and said by 2019 we'll have the baseline value, but by 2030 I want to have the percentage of vehicles that will be gasoline will be the total number of vehicles in the baseline. That's what this code here, this expression here means. The total number of vehicles in the baseline minus 108,000 divided by the total number of vehicles in the baseline of all fuels. This value here is the total number of gasoline vehicles. This value here is the total number of vehicles absolutely. So this is calculating for us the percentage in 2030. And you can see here that the number of gasoline vehicles decreases, our number of CNG vehicles increases. And we've done the same for LPG. We want 240,000 fewer vehicles that are LPG in 2030. We need to calculate that as a percentage, and that's what this equation does here. So those are the mitigation measures that we've calculated so far. I'm going to click Save. And let's run it again. I want to show you how we can view the results this time. And this time with viewing the results, I want to show you how we can look at the reduction in emissions for these different scenarios and look at the reduction in emissions altogether. To be able to, show what the benefit of these different mitigation measures are. Hopefully it won't take too long to calculate, because I'm not sure what to say while I'm waiting for it to calculate. So like I say, some of the mitigation measures, in the way that this analysis has been set up, are hard to model. For example, if we expand the number of vehicles on expand the metro, or we expand the bus rapid transit, there are things that we could do to make some assumptions to estimate what the effect would be, but it's a little bit tricky. Okay, so we've got our same graph here. This is for nitrogen oxide emissions, and we've got our baseline scenario projection into the future. We can see electricity generation probably makes up 20% or so of emissions. If I look at my renewable electricity plan, I get a small reduction. If I look at the existing electricity plans, which have much more solar being used, I get much bigger reductions. That's why I like this existing electricity plan scenario better than the other one in terms of a mitigation scenario. It's more specific rather than just an overall target of 25%, and it leads to a bigger reduction in NOx emissions. If I look at my biofuels transport scenario, there's an increase in NOx emissions, very small increase in NOx emissions, because switching to biofuels leads to an increase in NOx emissions. But if I look at CO2, we see that it's pretty effective. And if I went to biofuels 2, I get an even bigger benefit. And if I look for something like PM2.5, I get a small reduction in PM2.5. Black carbon, again, very small reduction from biofuels. Let's stick with black carbon and look at decreasing the average age of the fleet. That's more effective in reducing the emissions. It's still not the best thing that we could do to reduce black carbon, because the transport sector makes quite a small contribution, but we can see we really do decrease that contribution from the transport sector. And again, CNG conversion, there's a small benefit, but not much. And the small benefit for carbon dioxide. For NOx emissions, maybe there's a little benefit as well. But then it's really the all measures scenario. What happens if we do all of this? How much can it reduce emissions? And what's nice is that we see a relatively large benefit. I can view this as a table and I can calculate, so I'm going to just do every 5 years. I can calculate the benefit, 19,000 tons compared to a total of 94,000. So if I do 19.29 divided by 94.36, implementing all of those measures will reduce NOx emissions by 20% in 2030 compared to a business as usual scenario. If I look at carbon dioxide, for example, implementing all of those measures, 7.84 divided by 34.67 would lead to a 23% reduction in CO2 emissions compared to a baseline scenario, which is not bad. For black carbon, it's maybe slightly less. Let's have a look. 224 tons divided by 4085. It's a 5% reduction. So our reduction is different for different pollutants. Why is it less for black carbon? Well, if we look for CO2, we see that electricity generation and transport are two of the major sources. And if we look for NOx, transport and electricity generation, also two of the major sources. They're the only sectors where we've implemented any mitigation measures in this analysis so far. Black carbon, transport is a small source that we're controlling well from these measures. But industry, we haven't done anything in. Residential and waste, charcoal making, we haven't made any mitigation measures there. The same for methane. Agriculture and waste are our two largest sources, and we haven't put in any mitigation measures there. So in terms of the way forward, it would be great if you had any questions or let me know what you think about the analysis so far. I'll write an email, but I was going to suggest that we could begin to develop a report on mitigation of short-lived climate pollutants and air pollutants from climate change mitigation actions, where we can highlight these mitigation measures and we can, add in other results as we get them. I wonder if you think that would be useful. Thanks very much for watching. I hope it was clear. Please let me know if you have any questions, and I hope you have a nice day.